Okay, for this video, we're going to look at the formal mathematical definition of what it means to write the limit as x approaches a of f of x is equal to L, where a and L are real numbers. We've of course talked about some limit questions where we have different kinds of answers, where the answer to our limit question might be infinity or negative infinity, and we'll look at those definitions later. They are similar but not exactly the same as this definition, so we'll talk about those at another time. This definition involves a couple of Greek letters that you might not have seen before, a lowercase epsilon, which looks sort of like this backwards 3, and a lowercase delta. And so sometimes you'll also see this definition called the epsilon delta definition of limit. So one important question to answer before we get into the details of this definition is, why are we doing this? You already know how to use graphs, tables, and theorems to get answers to limit questions. So one answer is that as you move up in your math education, you should be becoming more and more of a careful reader, listener, and thinker about the math that's presented to you in your book or by your teacher. And if you are already pretty careful, there are a few things that should have bothered you about what we've done so far with limits. When we've been talking about limits, we've been talking a lot about x being close to a, but not at a. But that's a pretty vague notion about what does it mean to be close and how close is close enough. One other thing that we've used a lot when we're talking about limits is theorems. And it may have been a while since you've really looked at theorems in detail in math, but a theorem is supposed to be something that is proven to be true based on definitions and axioms. And we started using a bunch of theorems about limits without any proof at all, or even really maybe a clear definition of what it is that we would be trying to prove. Okay, so we're going to look at a couple of things on this picture and think a little bit about the definition informally with using this picture before we get to the formal statement of the definition with all the big details. So on this picture there are a couple of places labeled on the x-axis and y-axis. I'm going to label the one on the x-axis as A and the one on the y-axis as L, so that what we have here is really a picture of what it might look like to have the limit as x approaches a of f of x equals L. You might notice that there's not actually a point on this graph at a comma L. There could be a point there, but I just left it as an open circle to indicate that there doesn't have to be a point there at x equals a. Alright, so on the definition, when we write the limit as x approaches a of f of x equals L, it means that if we get close enough to x equals a, but not at x equals a. So we're going to indicate that here on the picture a little bit. So that would indicate some distance around x equals a. And typically when we think about these distances, I mentioned that there are a couple of Greek letters, and the delta is used to indicate that distance in the x direction away from a that the x coordinates are allowed to be. So at the right end of my interval here would indicate an x value of x equals a plus delta. So delta would be the distance away from a in the right direction. And then if I go to the left from a, delta units, the point at the left end would be a minus delta. So just by tradition, the delta distance is used in the x direction. And so that definition says that if we get close enough to x equals a, but not at x equals a, all the y coordinates of the function will be as close as we want to L. So if I kind of look at these places here and think about how close that's going to force my y coordinates to be to L, we can see that they're going to be pretty darn close to L here. So we have a little distance around L here. And one important thing about this definition, just to streamline things and to emphasize that we're really talking about distances here, all of these intervals I'm drawing here are symmetric. So just like this interval in the x direction, I went delta units to the right and delta units to the left. Also, this little interval I have here in the y direction, I'm going to have a distance in the y direction and label that the same amount of units up as I went down. So this is where we use the epsilon, so that distance in the y direction up from the L would be L plus epsilon, and then when I go down below the L, I would be at L minus epsilon. So by tradition, delta on the x-axis, epsilon on the y-axis. Alright, so here we're going to get into the guts of the definition. The definition at the very beginning says for every epsilon greater than 0, and it's important that you understand the definition starts with an epsilon. So that epsilon can be any distance in the y direction from our L, no matter how big or tiny we want that distance to be, but it has to be an actual distance away from L. That distance can't be just 0. So on our picture over here, on the last picture, we had these points labeled, so I'll go ahead and relabel them here. I've got L here, and then epsilon would be a distance both above and below L. So at the top here, L plus epsilon, and then the value below would be L minus epsilon right there. Okay, for every epsilon, there exists a delta. We'll label that. Remember, that's a distance on the x-axis, such that whenever x is within delta units of a, but not at x equals a, the f of x values will be within epsilon units of L. So I'm going to go ahead and follow these L plus epsilon and L minus epsilon values over to the graph of my function, and then down to the x-axis here to look at that appropriate interval in the x direction. Okay, and our A is this point that's labeled here. So one important thing about this graph that I drew here is that it's not exactly symmetric. I have an interval here, or some dashed lines here, that give me an interval that isn't symmetric. It's a little bit longer on the left side than it is on the right side. But remember, we're going to use that delta for that distance all around A. So I need to make sure that the delta I choose works for both sides. So I'm going to use the smaller side here to choose where my delta is. Use the smaller side to choose where my delta is. So the delta that I'm going to use is right there, A plus delta, and then A minus delta would be delta units left of x equals a. So it's the same distance away from A, left and right, and I use the smaller side because if I use the other side where these dashed lines are, that would have been too big on the right end. Okay, and if my x's are in this interval, that will ensure that the y's are in the interval we chose, no matter how small that epsilon is. All right, so you can write the definition this way. We've got a little picture here of what that definition represents. But when you actually use this definition to do problems or proofs, you usually would like some math symbols. And so we're going to take part of this definition and translate it into mathematical symbols. So we're basically going to go from where it says whenever to this comma right at the end and translate all of that into mathematical symbols. We're going to start here with the part of the picture that says x is within delta units of a. Over here on the picture, you can see that that would mean that a minus delta is going to be less than x, which would have to be less than a plus delta. So again, we could say that we have x between a minus delta and a plus delta. All right, I'm going to subtract a from everywhere in that inequality just to rewrite it a little bit. So when I subtract a from the left end, I'll be left with delta. And in the middle, I'll have x minus a. And then on the right end, I'll have delta. And this might look like some of those inequalities we worked with when we did the review material. This is an inequality that can be written with absolute values. So usually in the actual statement of the definition, instead of writing everything out in words, you'll see a statement that involves absolute values that says the absolute value of x minus a is less than delta. All right, so I have some symbols I've written here that indicate x is within delta units of a. But I also need to add something to that inequality that would indicate x is not actually equal to a. So when I write something that indicates x is within delta units of a but not at x equals a, we'll actually have something written that looks like this. So we're going to write something that means x is within delta units of a That's what this part of the inequality means. But if I want to say that x is not actually equal to a, I can also add to that inequality and say that that distance between x and a has to be greater than 0. So that allows us to basically say x minus a cannot equal 0, or x cannot be at x equals a. All right, and then kind of similar to what we did with the inequalities for x, we can do a similar thing with the f of x values and epsilon and L, and I can write an inequality that says the distance between f of x and L has to be less than epsilon. And for this one, I don't care if the f of x value is actually at L or not, so I don't need to add a left end to that inequality. I just need to say that the f of x values will be less than epsilon units away from L, or within epsilon units of L. So the part that I have in brackets on the definition, whenever x is within delta units of a but not at x equals a, the f of x values will be within epsilon units of L, can be written using these two inequalities, but we also have an if-then statement there. The whenever indicates an if-then statement. So that would say, if I have this statement about the x's, then that implies, this symbol means implies, it's an if-then or logical implication, that f of x is within epsilon units of L. All of that is what it means to write that definition of that limit that we've been working with for a few days. This definition is important to memorize. You can either write it out in words or you can write it in symbols, but you'll see that in some of your assignments and you'll want to make sure that you memorize it.